Welcome to Spring LIB.
31.60. So we have an RLC circuit that's being driven here. These are the values of all the things. And at 0.442 milliseconds, we want to determine what the power being delivered by our power source here is, or the generator or whatever. And then we want to find the power in the capacitor, the inductor, and the resistor, and then determine whether the sum of these is equal, less than, or greater to the power that the generator is delivering. So first what we want to do is determine the current in the circuit. It's going to be the same for all of the elements because it's a series circuit. So the impedance is going to be the usual formula here. R squared plus omega dL minus 1 over omega dC squared. Close up our square root. Try not to run out of space vertically. All right. So this works out to 1.93 amps. And the phase is the arctangent of the inductive reactance minus the capacitive reactance divided by the resistance. This would be 46.5 degrees. And so the current as a function of time will be I sine omega dt minus the phase, and we just found the amplitude of the current and the phase. So now the power supplied by the generator is just the current at that time times its voltage at that time. This is going to be I times E sub m times the sine of omega t minus phi times the sine of omega t. So we know what all of these are. Omegas are 3,000 radians per second, t 0.442 milliseconds, phi 46.5 degrees, etc. So we find 41.4 watts. So now for the capacitor, the voltage across it is V sub c sine of omega dt minus phi minus the pi over 2 radians we get from a capacitor. Negative Vc cosine omega t minus phi. And the amplitude of this, Ec, is just I over omega c. So now the rate at which we're adding energy to the electric field in the capacitor is the rate at which the energy is changing. This is the energy in a capacitor. Now the derivative of the charge is the current. So we end up getting I times Q over C. This is the voltage. Across the capacitor. So you'd already know what I of t is. We just found out what V sub C of t is. And so the rate at which the energy in the capacitor is changing is negative 17 watts. So the capacitor is discharging at this point in time. With our inductor, we have a similar story. It's the rate at which the energy stored in the inductor is changing. That's 1/2 L I squared. So this will be L times I times di dt. So we already know I is a sine, and so di dt is going to be a cosine. And then just to save ourselves a little bit of writing, I'll just mention that there's you get the product of your sine and your cosine, and then there's a trig identity you can use to find that it is this. It's just one of the product of the sine times the cosine identities. And so this works out to be 44.1 watts. So now the rate of energy dissipation in the resistor is I squared R. So we know that that's going to be I squared R, and then just the square of the time-dependent part of the current. So this is 14.4 watts. And now for part E, power for the inductor, the capacitor, and the resistor. We have 44.1 minus 17 plus 14.4 watts. So this adds up to 41.5 watts, which is equal to the power that the generator is supplying at that point in time, which is what we would expect because energy has to be conserved. And so if energy is leaving a system or an object or whatever, such as the generator, so Energy is leaving the generator. And so that energy has to be going somewhere. All of that energy has to be going somewhere else. And with the way that we've accounted for everything with this circuit, it has to be going, the same amount of energy has to be going into the resistor, the capacitor, and the inductor. Now, if we were looking at something like much higher frequency or something like that, you'd get into issues with, it emitting radio waves or something, and so you'd have to account for that, and it would be obnoxious. But in this case, we're at like a fairly low frequency, and we're just assuming that that doesn't happen. And so under the sort of idealized assumptions of how these circuit elements work and so forth, you can just add these up, and they have to be equal to the power that the generator is supplying.